All right, thanks for coming. Appreciate you being here. Happy Thursday. I know we've got the Easter break coming up, but for us, it doesn't really make any difference. So, oh well. A few reminders, the chapter 5, your like mini project homework is due tonight. Let me know if you have any issues with that. The project group decision is due by today. So if you don't have a group, I think, did I say you could do it by yourself? Yeah. Okay. Yeah. So if you plan to work by yourself, let me know. If you don't plan to work by yourself, let me know. I know I said that like you could put decide your own groups. I actually don't think you can do that. So I will need to put you in your groups. So I know there's one group who, and maybe it's you guys who are here. Um, but there is a group who made themselves in Canvas, but I have to copy it over to the assignment because it turns out that like in Canvas, it was if you make your own groups, those are like study groups and not assignment groups. Which okay. Okay, yeah. So I'll maybe just like at the end of class, I will um just copy it over. Not a big deal. But I would like to know what your groups are. And then the data source ideas is due by tomorrow. If you need it, I'm open to extending it to Monday night. So just let me know if you need that. And then we're doing the trees packet today, only a couple of problems. So I'm hoping we can get it done in class, or if you're not here, um, do it by yourself. And then tentatively I'll take it on Tuesday. So yeah, that's our plan. We're gonna go through the PowerPoint and the packet today. Let's open the right slides. Hello. All right, so my plan is we're gonna just kind of go through the PowerPoint and then we've got the packet problems, and so we'll split it half and half, or however that timing works out. So we're gonna talk about trees, which we already kind of know about. We're just gonna maybe talk about a few things in a little bit more detail. Where I also have a link for this in just so that you know like what the network's tree documentation looks like. So it's able to recognize like, is this a tree or is it a forest? A forest being a tree that like, if we have a graph, so a tree is connected, but if the tree is not connected, then it's a forest, which I think is a fun naming quirk. Because if we have multiple trees, then we get a forest. So there's all these different kind of things you can check with trees. So I just want to um, draw your attention. So there's like, you could do branchings if you wanted to, um, and find all this information. So this is available for you, especially thinking like for the project, if you want it. So we know some trees, there's some trees in nature that we can see, like this kind of graph where it's connected and it doesn't have any cycles. So we've seen the molecule before where everything's connected, but there's no cycles. So none of the molecules links back to another one. Um, we can also have like a literal tree where the literal tree has some roots, it has a trunk, and then branches, and then leaves at the end. And so all of these kind of terms we'll talk about in terms of graphs. And then we can have like river tributaries, where it kind of branches out. And maybe, so I was thinking about this as I was preparing, and like maybe something like this where, let me draw. Like as the rivers change, maybe these two get connected. Um, so that I think that could be a possibility. But in the end, like if this does connected, if this does get connected, it doesn't go like the water doesn't flow back upstream, right? It's all going down to the ocean or something like that. Um, so maybe if we were representing a river as a graph, maybe this would be directed to represent the flow of current. They also have an example of this kind of artificial tree where, let's say we have some pipeline distribution network where it starts at one location and then we're pushing this material out to different areas. And so some take this path, some go all the way down over here. And so this is a tree. There's other formulations of trees. We can have like a family tree. So this one was like, what was this one? It was like a family tree or something. The family tree of Saxon kings in the 9th century in England. So the idea of like Egbert is the parent of Ethelwulf, who's the parent of all of these people. Alfred the Great is the father to Edward the Elder, and so on. And so this is a tree. We can also have these hierarchical trees where, like, if this is a company where we have sales assistants and they report to the director, or the warehouse assistant and the coordinator reports to the manufacturing director, where sales and manufacturing are like two separate aspects. Let's see if I can think of, so like at St. Mary's, there's like professors, and the professors all report to the department chair, who reports to the dean. And so there's different like departments, and like in the School of Science, all of those department chairs report to the dean. And so we can draw the hierarchy that way too. So our definition is that a tree is a connected graph with no cycles. So that's the simplest version. The book lists some equivalent definitions. So all of these end up being equivalent. We won't look at the proofs, but if you want to look in the book for the proofs to convince yourself, go for it. But these are all equivalent statements, right? So T is connected and has no cycles. That's just the same as that first one. T has n-1 edges and no cycles. It's kind of saying the same thing, but instead of connected, we're saying that it has n-1 edges. T is connected and has n-1 edges. This is one that as I was looking through this, I was like, that's not true. Like, that's not equivalent. And so I tried to draw something like if I have 4 vertices, and I try and draw a cycle, but then it's not connected. And so I thought maybe like, haha, I've disproved it. But this actually has 4 edges and not 3 edges. And so in order to make it connected, we have to have something like this, or have to have something like that. So for it to be both connected and have n-1 edges. The other ones are that T is connected and the removal of any edge disconnects T. And so when we've got that, then that means there can't be any cycles, because if there were to be a cycle, like something like this, removing any one of these edges isn't going to disconnect us, right? So it needs to be a tree and have that risk of, now if we delete this edge, the graph will be disconnected. An equivalent definition that any two vertices are connected by exactly one path, or it contains no cycles, but the addition of any new edge creates a cycle. So if we were to add an edge here, either way we go, then it makes a 3 cycle. So adding any edge creates a cycle. So those are all our definitions. We'll talk briefly about a spanning tree. So if we've got a graph, just any graph, not necessarily a tree, a spanning tree is a special type of tree where it's a subgraph of that original graph that includes every vertex, and the subgraph is also a tree. So let's look at some examples. So this is our graph. It's not a tree. It's got cycles. But this is a spanning tree because it has all of the vertices and only some of the edges, and the edges that are there make it a tree. This is also a tree where we maybe everything goes around Y and radiates outward. This is also a tree, maybe in a kind of U shape. And so these are all spanning trees. They're different spanning trees, but they're all still spanning trees. So the book gives two main ways to get a spanning tree. One is where you build up. And so here, you select edges of the graph one at a time, and you choose the edges that won't cause there to be a cycle. And you keep choosing edges until you've gotten all the vertices in. So they got this spanning tree by doing, so first they chose V and Z. So they chose that edge, and then WX, WX, chose that edge, and then XY to get in the middle. And so now we've got all vertices, but they're not connected. So it's not a spanning tree yet. And so we just add that edge Y to Z. We could have also added the edge V to Y to get there too. That's just, we chose one of them. The other method is the cutting down. So as opposed to building up where we choose edges to include, cutting down means we choose any cycle. So as long as there's a cycle, let's choose one of its edges and throw it away. So if we start with this graph, what they did here is they're like, let's get rid of that edge. And then, so that's not a cycle anymore. Neither is that. But now there's a 4 cycle, V, Z, Y, W. And so if we get rid of Y, Z, then we have that. So now the left half of the graph is open. And so just get rid of the edge from X to Y, and we're good to go. So that's how to get a spanning tree. It's going to change when we look at weighted graphs. There are specific algorithms, because when we look at weighted graphs, sometimes what we want to do is find the minimum, so the minimum cost. Those of you in 374 should be familiar with this. So it's for an unweighted graph, it kind of doesn't matter maybe, but for a weighted graph, it might matter because you may want to minimize the cost or maximize the cost of the spanning tree. So there's an idea of rooted trees, which is where we have our kind of anchor for the tree somewhere. So for this one, it's the managing director is the root. But really for any tree, like even a path, we can just, if we're looking at the tree, we could make a decision and say, that one's the root. And so then we can draw it like that now. And that tells us that that's the root. And so we're going to do some operations which depend on this node being the root. Sometimes the node that we choose is arbitrary. Sometimes it comes to us from the data that we choose. So like here for the managing director, that makes sense for the director to be the root. So there's a difference if you probably are familiar with a binary tree or a binary search tree. There's a difference between just a rooted tree in general, so that doesn't it doesn't have any restrictions on the number of children, where like this is the parent and these are the children, which is just communicated in how we draw this. For a general rooted tree, it doesn't matter how many. So like this parent has 3 children, this has 4, this only has 2, this has 3. These guys only have one child, this one has 3. So there's no restriction, right? We can have as many as we need or want. A binary tree is where each parent, each node has at most 2 children. So at most 2 children. And then further, if these nodes have some data associated with them, like if they're numbers or letters, then we can add in the binary search tree property, which is where we say that if we go left, then it has to be less than. If we go right, the data in the nodes has to be greater than. So that's just an added element that we add on top of this binary tree. So it's another property that we enforce if we want to. We can also keep track of like experiment outcomes with a rooted tree. I think this is pretty fun. So like if we've got a coin, if we flip it, it's either going to be heads or tails. And so this tree represents us if we did this experiment 3 times. So 1 for each level beyond the root. So the first one is we flip a coin and it's either heads or it's tails. Then if we flip the coin again, this shows us the possible outcomes, where either we get heads, or we get heads, tails, if the first one was heads, or if the first one was tails, then we get either heads or tails from that second one as well. And then we can make a whole nother level for our third flip. So either we get heads, tails, and so on. So we can keep track of these different outcomes. I think this one was kind of cool. So this one was if we assume that we're playing tic-tac-toe against someone and someone puts an X in the middle, then we can keep track of our strategy, like how do we win based on this? And so our options are either to put an O in a corner or in this like the cross of the board. Considering, and it considers that these 2 moves are equivalent, I think you can just rotate the board to fit what actually happened. And so then it goes into the other possible moves. So either X then goes in the corner or on the side that's not on the same side as the O, or in the corner in line with the O, or right next to the O. And then there's other possibilities for where they could go if we had placed the O right next to the X. So there's different strategies. And so we could further expand that tree if we wanted to figure out what are all the possibilities for how we could play tic-tac-toe. So we could like fully map out this game to see what are all the possibilities. There's also trees in grammar. Does anybody remember like diagramming sentences in, was it like third or fourth grade? Something like that? No? I was homeschooled and my mother made me diagram sentences and I hated every moment of it. Um, but yeah, so this idea where we can like break a sentence into its parts of speech. And if you, I don't know who went to the talk yesterday, but there's kind of like this notion in computer science and programming languages as well, where it breaks down if any line of code that you type, the compiler breaks it down into the different parts and it says, okay, you're defining a variable here and we have an equal sign, that means an assignment. And so the compiler breaks it down in order to understand the code that you actually typed and make that happen under the hood. But in terms of English, we can do this as well. So in here, we've got the sentence, good students read books. And so we can break it into like a noun phrase and a verb phrase. And then we've got the noun of students and good is an adjective. Read is a verb, and then books is a noun as well. I had to stare at this for a bit when I was making the slides, but there's a sentence that they give of council rents rocket, which is just 3 words, but can have different meanings depending on how you assign the noun and the verb. So one possibility is that there's an entity called the council, and the council is renting like a rocket ship. And so the noun in that case is council, the verb is rents, and then the noun is rocket. The other possibility is that since the people who wrote this book are British, then like the council is, I think like the local area. And so the local area, the cost of rent is dramatically increasing. And so in that case, the rents turns out to be the noun. So like the cost of renting. And then rocket is the verb where it's increasing. So it depends based on what we're actually trying to say. We can represent data structures as trees. So they gave this, so like binary tree, I feel like is very obvious, where for binary trees, we've got roots. For stacks, I guess this could be like the top of the stack maybe, where we can just, if we have all this data, then it's just a path, which maybe isn't very interesting, but we can formulate it in this way if we need to. They had this, which I think in England, so we've got zip codes and they've got postcodes, and I think they're alphanumeric, which that makes sense. Like if we start with MK and then it goes to MK1, and then it's like lexicographic ordering that way. I think since our zip codes are numeric, it maybe doesn't quite translate to this, but it's a possibility. So the other thing they have, and this is also one of the problems in the packet of, let's say we have a tree like this where we've got maybe section 8, and then it goes into sections 8.1, 8.2, 8.3, and so on, where like 8.1.1.2 lives under section 8, subsection 1, subsection 1, and it's number 2 of this 4th level. And so there's different ways we can keep track of this. So maybe we use trees to keep track of parentheses. So like 8 is the fully outer parentheses. And then as we keep moving in, this tree helps us keep track of which set of parentheses are we at. We can also say that this is representing subsets of a set, where like this whole big circle is 8, and then we've got 8.1 inside here. 8.2 is kind of off by itself. 8.3 has 2 subsets, and so that's 831 and 832. Or it corresponds to the sections of a report. So where we can have this structure like that. Okay, so that's all I have for you, just kind of showing the pictures the book has, because I think it's fun and interesting. So now we've got the packet, which should be on Canvas. So slides are there, the packet is also there. So my plan for the rest of class is to work on the 5 or so problems and turn it in at the end if you finish it, or give it to me next time if you didn't. Okay, so I will pause the recording, go around and give people who showed up a packet, and we'll be good to go. Make sure that you let me know who's in your group today and the data source ideas for due tomorrow, but if you need time, I'm happy to extend that to Monday if you need. Any questions? Okay, let's go.